Greetings. We will resume our discussion on the differential scattering cross section, and we had considered a plane incident wave, monoenergetic pure plane incident wave, for which we know that the differential cross section goes as the square modulus square of the scattering amplitude. And what we had employed to arrive at this expression was a strictly monoenergetic wave, which we resolved into partial waves, right. So this was the resolution which we employed, and then we got the scattering phase shifts and so on, and then we got the expression that the differential scattering cross section per unit solid angle d sigma by d omega is given by the modulus square of the scattering amplitude. Now this is clearly an idealization. Okay, in a real situation you will have not just a pure single momentum vector, but you will have a collection of momentum vectors, and they will all be in the neighborhood of a given energy, but not exactly at that energy, and they will not be exactly at the same momentum vector, because momentum is h cross k, so there will be a little bit of spread. So this idealization is not the real situation that you expect to meet in a scattering experiment. A real incident wave will then be a superposition of plane waves of this kind, okay, because there will be several of them, and this omega, which is frequency, will in fact depend on k according to whatever is the dispersion relation. So there will be a little bit of k dependence of omega. So you will have to take that into account and ask the question, if this expression d sigma by d omega equal to square root of modulus of the scattering amplitude, is this expression valid also for a realistic incident wave packet as it is for a strict ideal monoenergetic wave. So that is the question that we began to discuss in our previous class, and we will continue our discussion of this particular point. So this is the incident wave, which is a superposition of waves of the previous kind. This amplitude in general is complex, so it will have a real part and a phase part, okay. So a complex number you can always write as rho e to the I theta, where rho is the size of that particular complex number, right, and alpha will be the phase. So you can write this in terms of this rho e to the I theta kind of structure, and with this structure you have the phase which consists of this k dot r minus omega t. This phase must be expanded to include this k dependence of alpha, which is coming from the phase of this complex amplitude A, and you have a net phase which is k dot r minus omega plus alpha, okay. So this is the total phase of this particular term. Now the question is, if you have the incident wave packet which is reaching the target, so that you know there is an encounter and scattering takes place. Now you do know that when you have a number of waves, when they reach a certain destination, like if you have waves coming in from a source, there is a screen, it may have some holes, even if it is an incident optical wave, if you like, right, and there is this incident, you know, if there are holes in the screen, and then you have got a detector screen, then the intensity that you find on any point on the detector screen is just a superposition of what you get from all of these holes, right. So essentially all of these waves have to have a superposition principle which they must observe. Waves do observe. Now this is the fundamental principle of linear superposition, which is applicable to all wave phenomena, and we also know from the superposition formalism that if waves with equal amplitudes reach a particular point of the detector in opposite phases, they can kill each other or else they can augment each other, right. So, there will be some sort of interference and they could actually in principle kill each other, and since you are performing a scattering experiment in which the incident wave packet reaches the target, you ask the question, what is the condition under which this incident wave will be the largest, so that these phase factors, because this is oscillatory beta k, and depending on k beta will change. So, for different values of k it is possible that these oscillations cancel each other and you will not have a net resultant intensity. So, the condition that this phi is the largest is that these oscillations should not kill each other. In other words, this particular condition which is leading to the cancellation is taking place because beta is a function of k, and this condition should not be satisfied. In other words, because the cancellation is coming because the different components in the superposition have got a net phase which depends on k, the condition for non cancellation is that these oscillations should not happen, and therefore beta should not change very much with k. And if beta is not to change very much with k, what it means is that the gradient of beta with respect to k must vanish. So, that is the mathematical condition that must be satisfied, so that you have a net wave packet, right. So, this is the condition that you are looking for, and let us ask if this condition is satisfied. So, this is the condition for the incident wave packet to be the largest. This condition is that the beta gradient must vanish, gradient with respect to k must vanish. Beta is given by this k dot r minus omega t plus alpha, as we have seen. K dot r is, let us say, kz, that is by the choice of the z axis in the Cartesian coordinate system. R cosine theta is what we call as z, okay. So, that is the orientation of the polar axis, and if this were just a one dimensional problem, our condition for phi incident to be the largest would be that the derivative of beta with k vanishes in one dimension, right. So, what is the derivative of beta with k? You get a term from here, then you get minus d omega by dk, and then you get d alpha by dk, and these derivatives you evaluate as at a certain incident momentum, okay. So, this is the condition that you would get in one dimension, and you can rewrite this as z is equal to d omega by dk times t minus the derivative of alpha with respect to k. So, that is your condition which must be satisfied, and you can easily generalize it to 3 dimensions by writing, instead of this Cartesian component z, you write the full position vector instead of this derivative and the second derivative, the derivative of alpha, you use the corresponding gradients with respect to k. So, that is the automatic mathematical generalization from 1 dimension to 3 dimensions. So, this is your condition that the position vector is given by this term which you will recognize, this is the gradient of the circular frequency omega, and you know that this is the velocity of the packet, right. So, you have the velocity of the packet which is appearing here as the gradient of omega with respect to k, and this is vi. You can shift the time origin to t0, whatever it is. So, instead of t you have got t minus t0. So, you have the position vector equal to velocity times, instead of just time t you have t minus t0, and this minus gradient of alpha is what you call as r0. That is obviously a position vector, it has got the dimensions of length, and this is how you define a certain r0. This r0 is related to the gradient of this phase alpha. So this is defined along with a minus sign, which is why you get a plus sign here. So let us use this result in our expression, and these are our, this is the complete phase, and we now look at how omega depends on k, because the gradient of omega has already appeared in our expression, right. So the gradient of omega, the group velocity, will depend on what kind of k dependence the circular frequency omega has. Okay. So let us write this expression. So let us expand omega k about a certain incident direction ki momentum vector, and this is the first term, leading term, plus the gradient of omega with respect to k at that particular value of the momentum, which is ki, times the difference from that momentum vector, that is the first term, and then you will get higher order terms coming from second derivative, third derivative, and so on, right. So for the time being, let us ignore those higher order terms, and we are going to of course ask the question if we can neglect the higher order terms. So we will discuss that question in a little while. In the meantime, let us see what form this takes. So the gradient of omega is the velocity. So you have got the dot product of this velocity with this difference in momentum vector in units of h cross, and you get two terms, one is vi dot k, the other is minus of vi dot ki, which is here. So you have three terms over here for omega, and we do know in fact that omega, what depends, how it depends on k. Omega is E over h cross, so it is h cross square k square over 2m. So if you take the gradient of this quantity, okay, h cross square k square over 2m into 1 over h cross, which is what omega is. So what do you get? You get the product of h cross over m and the k vector, right. This is just the particle velocity. So that is the group velocity and the particle velocity, they are the same. So we know what omega is in terms of k. So we get this group velocity which is equal to the particle velocity, and you can use this form h cross ki by m to get this term. What is this? Vi dot ki, but Vi is along ki, so you get a ki square multiplied by h cross over m. So you have this term h cross ki square over m, and what is h cross k square by m? It is twice this value. This is h cross k square over 2m, this is h cross k square over m. So this is twice omega. So that is what you get, right. So you can put twice omega instead of Vi dot ki, and that gives you an expression for omega in terms of the momentum vector k, which is omega as a function of k is given by this first term omega ki, then you have got the second term which is Vi dot k, you have got the third term which we know is with this minus sign, it becomes minus twice omega ki, and there is a minus twice omega here, there is a plus omega ki over here. So these two will give you a minus omega, and that is the net result that we get, of course assuming that higher order terms are neglected, and we will come back to this question. Okay. So this is your expression for the k dependence of the circular frequency, and now you put this omega into t in terms of these two terms, minus omega into t plus Vi dot k into t. So Vi dot k into t, but there is a minus sign here, So, you get plus omega into t minus Vi dot k into t, right. So, that is a mere substitution of these two terms over here, and then you can combine the terms r minus Vi dot k. So, you have got the Vi dot k is coming in the second term and this is multiplied by t. So, you have got a k dot r minus Vit, you have got omega kit coming from here and the alpha k coming from here, right. So, we bring it up to the top of the next slide. And you also now have to consider, in as much as you considered the momentum dependence of the circular frequency, you also had the gradient of alpha. Okay. Now, what is the gradient of alpha? So, this alpha also depends on k. So, you can expand it about the initial a particular momentum vector ki, which is the incident momentum vector. I is the subscript corresponding to the incident momentum vector, and if you expand it about this, you get a leading term plus the gradient with its scalar product with the difference in the two momentum vectors in units of h cross plus higher order terms, and again you will ask if the higher order terms can be neglected. So, it is the same question, but we will answer the two questions together. So, we already have identified this as our minus r0, the gradient of alpha. We introduced r0, it has got the dimensions of length and we have defined our r0 with a negative sign here. So, we will write this as negative r0, and along with this you have these two terms over here. This alpha k is replaced by these two terms, first term and this r0 dot k minus ki with a negative sign. So, these are the two terms that you should put in your complete wave packet for the incident beam of particles. So, there are a number of terms which go into the phase, all of these together constitute the phase and they have only been separated over here. So, these two terms r0 dot k is here and then r0 dot ki is here with a plus sign, okay, because there is a minus sign here, there is also a minus sign here. So, it comes with a plus sign here. So, this is your complete expression for the incident wave packet. We bring it to the top of this slide now, and what do we have? We have the sum of these terms, which is nothing but alpha k, and we can rewrite in an equivalent form in a slightly compact notation. We first separated it, now we recombine it just to write it in a more compact form, but we separate it to recognize how the gradient of alpha is coming into the picture. Okay. So, this is an equivalent form of the incident wave packet, and we recombine this in the original term, because this modulus of A into e to the I alpha is what you had for the complex amplitude, which scaled the different momentum dependent plane waves. So, it is just a recombination of these terms to keep track of what the phases are. Having done this, you factor out e to the I omega t minus t0 from the integrand, because ki is a particular unique incident vector, it is not changing. So, it is not a variable in the integrand, it is a constant under the integrand. So, you can take it out of the integration. Okay. So, this phase corresponding to the incident momentum vector is pulled out, and this is t minus t0, there is already an omega t here, and because there is a minus t0 which is pulled out, you must compensate for it by inserting it in the integrand. Okay. Now, if you put t equal to 0 in this, you get the incident wave corresponding to t equal to 0, okay, and notice that these two are of the same form, they have exactly the same form. So, what you have in this red loop is something very similar to this, with the difference that the time is shifted to t0 and the position vector is also shifted, because instead of e to the I k dot r, you have got e to the I k dot r minus vi times t. So, depending on how much time has elapsed, the position has elapsed, and except for that it is exactly the same wave packet. There is no difference except for a shift in the time and a corresponding shift related to the position of the wave packet. So, it is exactly the same form, which means that you can write this incident wave packet at an arbitrary time in terms of an incident wave packet at time t0 by recognizing this r0 plus vi t minus t0 to be equal to r of t, because you have got r minus vi t here. So, this r minus vi t is what you call as r0, and with this r0 you have got exactly the same wave packet, it is only shifted. So, this is the realistic incident wave packet that we are working with, that is the one that we started our discussion with. We factored out this term and we look at the value at t equal to 0, recognize the identity in the two forms, and our essential conclusion from this is that you have got a free wave packet which is centered around r0 at time t0. It will have exactly the same shape as a wave packet which was centered around a different point in space, and where it is located depends on how much time has elapsed from the reference time t0. So, it will be the group velocity times t minus t0. So, it will be displaced by that, and at a later time t. So, it will be exactly and identical. So, there is a shape function that you can expect to factor out from this analysis. So, let us go back to the question that we had raised, that we considered the momentum dependence of omega, and there were additional terms that we could have considered coming from the second, third derivative, etc., which we neglected. We did the same with reference to the phase alpha, which also had a momentum dependence, and in both cases we have thrown out the higher order terms, we have ignored the higher order terms, and we ask under what conditions can we ignore the higher order terms. Okay, this question we had raised and we need to answer this. So, let us take up this question and ask under what conditions can we ignore the higher order terms. So, let us look at this expansion. The condition to ignore the higher order term is that the first of the remaining terms which is ignored is the second order term, and if the second order term itself is small, then by induction you can argue that the remaining terms can also be ignored. So, let us be satisfied at just asking this question, that under what condition can you ignore the second order term. So, let us look at the second order term. The second order term, which is the second derivative of omega with respect to k multiplied by the square of the difference k minus ki. This is the second order term. This must be small, right? This is our condition. Is this condition satisfied? That is what our question amounts to. So let us look at how omega depends on k. We know that it depends quadratically on k, h cross k square over 2m. So the first derivative goes with k, and the second derivative is a constant, which is h cross over m. So instead of this second order term, you can replace the second order term by h cross over m, and you get h cross over m multiplied by this must be small, and this multiplied by the time will give you a dimensionless number, and that number must be equal to, or it must be much smaller than unity, so that you can ignore its powers. Okay. Now what is the time scale we have in mind? Because this term obviously becomes large as t increases, and if t increases to 10 hours, 20 hours, 20 days, 20 months and 20 years, 20 million years and so on, it is going to grow, right? And you cannot expect this to be less than 1. But what kind of time scales are involved? The kind of time scales that are involved depend on the velocities of these packets, because the only time which is of interest to us is the time it would take for this packet to reach the detector. Okay. Once it reaches the detector, you are done with the experiment. Okay. And any further time is of no interest to you. Okay. So the time that you are really dealing with is how much time it will take to reach the detector. So that depends on the kind of geometry you have set up for your apparatus in your laboratory, and those are the physical time scales which are of importance in this mathematical relationship. So the mathematical relationship is that this product of h cross over m multiplied by the square of the difference in momentum in units of h cross times time must be less than 1, and this time will depend on how much time it takes to reach the detector, and that distance in our geometry is capital D. Okay. But since the phase velocity is half the group velocity, all you have to consider twice that distance, right? And if this t is less than or equal to twice distance by velocity, then you are okay. And this is what it amounts to. So if this condition is satisfied, that h cross over k, this is delta k square, and instead of this time we have this 2d over vi. If this product is less than 1, then we are okay. So this is the condition depending on the distance. Okay. Now this distance d is a laboratory parameter. This is the distance from the target to the detector. So now you notice that you have got an h cross square over m and an m over h cross here. So these two terms cancel, h cross over m into m over h cross. So these two terms cancel, and your condition now is delta k square over k into twice the distance should be much less than 1. That is what your condition boils down to, and this is the basic uncertainty that you are aware of. The delta k times the uncertainty in the position, that depends on how much the wave packet is delocalized. So this is of the order of 1, this product is of the order of 1. So we will just do an order of magnitude analysis. So delta k is of the order of 1 over delta r. So this is delta k square. So this is 1 over delta r square, right? It is 1 over delta r square. So 1 over delta r square I take to the right. So, it becomes the square of delta r, and here I have got 1 over k, which is of the order of the wavelength. Okay. K is essentially 1 over lambda. So, you get from this delta k square on the left, you get delta r square on the right, and from this 1 over k you get a lambda. So, this condition is that lambda into twice d should be less than the square of delta r, or the corresponding square roots should have the same inequality. Okay. And this is what sets the time scale, because in a laboratory you have typically delta r, which is of the order of 1/10 of a centimeter, and this is of the order of 1,000th of a centimeter. Okay, both are length scales. These are the numbers that you deal with in most experiments, or in some other experiments this may change, but notice that 10 to the minus 3 is much smaller than 10 to the minus 1. It is 100 times smaller, and this condition is therefore satisfied in an experimental scenario, and therefore the condition that we needed to be satisfied so that we can ignore the higher order terms is in fact satisfied under laboratory conditions, and we can ignore those terms, we can ignore the higher order terms happily. This is satisfied, and whatever expressions we had, we can continue to employ them in our subsequent analysis. Okay, what have we got? So, this is the capital D that I was referring to. This is the length scale. Now, this is the transverse width of the wave packet, this is the longitudinal width. Okay, that is the kind of scales which are involved, and it is this distance. If this distance is farther, that is when the t will keep increasing, but how much d does it have to cover anyway? Okay. So, it has to get to the detector, and if it did that, that depends on what is the longitudinal width, and these are this is the kind of geometry we have in picture. You have got an incident wave which has got a certain spread, which is the longitudinal width, which is of the size of L, and then you have got a target which has got a certain tiny dimension of a, and this length is of the, this is about the size of the uncertainty spread for our order of magnitude analysis on the length scale, which gives you the corresponding spread in the momentum, which is inverse of this, right. So, this is the picture that we have under consideration. The other thing you have to recognize is that depending on how it is set up, you may not have the incident beam meet the target head on, but there may be a little bit of distance, because where it impacts the scattering region may not be exactly head on, there may be a little bit of displacement over there. So, there is a certain impact parameter that you may have to consider, and all particles described by the same B will have a similar shape. So, the wave packet, the exact detailed wave packet shape will really not matter, because this distance is quite larger than the target. Okay. So, our analysis is quite on comfortable ground, and detailed shape of the wave packet does not matter. So, you will have a scattered spherical outgoing wave, and the incident wave, the net scattering solution, as we know, is a sum of the incident plane wave and a scattered outgoing wave. This diagram is from Joe Shane's book, and you have got the net scattering solution, which is a superposition of the incident wave plus the scattered waves, okay, as we had even for a monoenergetic beam. So, that is what we considered already in details in some of our earlier discussions, but now we are trying to see how it gets modified, if at all it gets modified, does it change our primary results when you are dealing with a realistic incident wave packet, which is a superposition of plane waves around different momentum vectors, all momentum vectors which are very nearly the same, but slightly different from a pure value of the incident momentum vector. So, there is a little bit of spread, which is what generates this wave packet. So, this is the free particle wave packet. It is a superposition of free particles. Okay, e to the I k dot r minus omega t is a plane wave, it is a free particle. If it is not to meet head on, but there is a displacement because of an impact parameter b, this r must be displaced by r minus b. Okay. So, this is the same expression for a free particle wave packet, but it respects the impact parameter b, right. So, I have written this phi with a subscript b and changed this r to r minus b, other than that it is the same thing. So, it is the incident free particle wave packet taking into account the impact parameter b. The phases then consist of e to the minus I k dot b, e to the I k dot r and e to the minus omega t. So, these are the three contributors to the phase. Okay. This omega depends on k. So, if you consider this dispersion, because it is k dependent, you can write this omega in terms of these two terms, which we have already found. So, this is the free particle incident wave packet. Now, let us multiply the integrand by unity, it never hurts, right, and you can resolve this unity into these two factors. Okay, they are phase factors, they are the same factors, phase factors, with a plus sign here and a minus sign here, there is a minus sign here and a plus sign here, the same terms. Okay. So, you multiply the integrand by 1 and then you factor out these three terms, e to the I omega k I, everything which does not depend on k I can be pulled out of the integration, because the integration is over the variable k. So, k I under that integration is a constant, and anything and everything that has got k I alone can be factored out. The remaining terms stay inside the integral, and the net value of the integrand must be preserved, which is guaranteed by factoring unity into these two factors. So, you factor out these three terms, e to the I omega k I, e to the I k I dot r minus b and e to the minus I k I dot v I t. So, notice that what is pulled out of the integration has only k I and nothing else, and having pulled this out, whatever remains inside is what will compensate for these factors, so that you regenerate the original phase. So, it is just a little bit of very straightforward manipulation of the phase, okay, just rewriting the phase in this particular fashion, which is what will give us a very useful result. So, this is the same expression, you have pulled out these k I dependent terms which are constants in k outside the integration, the rest of the integral is here, and there is a k minus k I in both of these terms. So, you combine them. So, you have k minus k I times r minus b from this and v I t from this. So, you combine these two terms, okay, that makes it a little easy. So, it is just a rearrangement of terms that we are doing here, nothing very fancy, and essentially what you find is that this is the factor, this integration is what will have complete information about the shape of the wave packet. The remaining term is just a phase factor. So, this is the shape function. Okay. The entire shape is determined by this integral, which is defined as 1 over 2 pi to the power 3 by 2. This factor is absorbed in the definition of chi, and then you have got this triple integral in the momentum space of modulus of ak and this phase factor, which is a reconstruct of the original phase by factoring out appropriate pieces. Okay. So, what this rearrangement of the terms has allowed us to do is to introduce a shape function which is given by this chi, and if you notice that this chi, which is it completely defines the shape of the wave packet. Now, you remember that we had an original normalization which we agreed to, that we have this normalization, and this normalization is going to be valid for this particular expression. Out of this, this is just e to the I theta kind of term. So, the same normalization, because what is factored out of this chi, what multiplies this chi is just an e to the I theta kind of term. So, obviously you will get the integral of this shape function modulus square also equal to 1. Okay. So, this is a very simple property of the shape function which emerges from this analysis. Now, this is the free particle wave packet with an impact parameter. Let us write it explicitly. We have seen the phase factor to be e to the I k dot r coming from here, e to the minus I k dot b coming because of the impact parameter, and this is the omega t factor. This e to the I k dot r is because you are dealing with a free particle case, and we know how it will get affected if you have scattering, right. Because if you now consider the solution to the complete scattering problem now. So, this is the free particle case. If you have a complete scattering problem, then this factor e to the I k dot r must be replaced by the scattering solution with the outgoing wave boundary condition. So, this e to the I k dot r must be replaced by the solution to the scattering problem with an appropriate outgoing wave boundary condition. But then this is obviously different from the previous case of strict monoenergetic beam of incident particles. This is a realistic incident beam which consists of a large number of waves which have slightly different momenta corresponding to a slight difference energy spread. Also the directions could be slightly different, and you have got a superposition of all of these different momenta. So, this is the geometry that you have been considering, and the wave packet over this distance, okay, it will not overlap with the target when it is far from the target. Okay. When it reaches the detector, it will not have any overlap with the detector. So, this is the geometry you have under consideration, and with this the complete solution to the scattering problem, which for pure strict incident waves is given by this outgoing wave boundary condition. Now, for the wave packet you have got a similar expression as you had for the free particle incident wave packet, with the difference that the term over here, which was e to the I k dot r, must be replaced by the outgoing wave boundary condition, which is this, which will not be just the incident wave, but the incident wave plus the scattered wave. So, we will have to take that into account, and since we are out of time, I will stop here, and in our next class I will complete the proof that with this wave packet, which takes into account the impact parameter, for the complete scattering solution, the relationship d sigma by d omega equal to the square of the modulus of the scattering amplitude, this is still valid. Okay, this is the relationship that we set out to prove, which we started in our previous class. We are almost there, but in the next class we will complete the proof. If there is any question, I will be happy to take. Otherwise, goodbye for now.